Okay, so today we're going to learn what it takes to build a quantum computer. And here to speak to us is Dr. Lirakis?
Yes.
Chris Lirakis, who got his PhD from Northeastern University in 1990, actually in high energy physics, and then moved to BBN, where he got involved in quantum key distribution and was part of the formation of a quantum computing group there. He is now at IBM since 2012, where he works to help IBM basically build quantum computers and distribute them all over the world. So take it away.
Yeah, so I mean, just one of the responsibilities I have right now that's giving me a lot of anxiety. I think you guys probably saw the announcement that IBM is going to put a quantum computer in Germany. That's my job. And so I'm figuring out all the bits and pieces. In some ways, it would be fun to do like a live Zoom off my cell phone and give you a virtual tour, but maybe that's another time. Anyway, let's get into it. What I'm going to talk about, because as I said earlier, as I was having kind of colloquial conversation with you, didn't know kind of the full makeup of the audience. And by the way, I want to encourage people to interrupt if they have questions. That this should be interactive. It's more important that your questions are answered and that you kind of get things out on the table rather than me just speak to you. But I'll give it like a brief introduction to what are quantum bits. I'm going to give the IBM roadmap. You can ask questions during that. Talk to you a little bit about superconducting qubits in detail, some hardware challenges, some skills that are necessary to scale, talk a little bit about the software and some about the problems of interest. And all throughout this, the underlying theme that I will keep coming back to over and over again is workforce development. In order for a lot of this to happen, we're going to need skills from all over. It's not going to be built on the backs of physicists alone. We're going to need engineers. We're going to need mathematicians. We're going to need mechanical engineers. I'll point out, obviously from the super fridge, you kind of get the mechanical engineering portion of that. And you need software people. You need all manner of people. But it helps, even if you aren't an expert, to have an armchair knowledge of what quantum computing is, and that enables you to figure out how do you fit into this larger picture, or how might you fit. So in terms of quantum bits, and forgive me if you guys have seen this before, but you talk about classical bits, and classical bits are always 0 or 1, and when we want to have a quantum bit, this came up in kind of initially in a conference in 1982 at MIT. It's the idea of putting a 0 or 1 on a quantum state. So you say that's a quantum level. So you guys all know about, I'm sure you've done this experiment at some point in your lives where you did an ionization of, say, a hydrogen atom or something like that. You can look at the Balmer lines. Well, that's exciting various quantum states. And we just say, out of those many lines that are there, we're going to arbitrarily assign the 1 state of, or the 0 state of being the ground state, and the 1 state being one of the excited states in there. And depending on what type of bit modality you're using, whether you're using ions or neutral ions, charged ions, superconducting qubits, spins, they all do this, and just in different ways. But what's one of the difference between, say, a classical bit and a quantum bit? The classical bit, you can only have a 0 or 1, and the quantum bit, you've got a complex set of variables, as long as it's normalized, because it's a probability density function, that you can now have a arbitrary kind of space. And this graphical representation on the right shows you the way we think about things. This is called the Bloch Sphere, after a physicist from the late 40s, I guess. And so 1 is at the South Pole and 0 is at the North Pole. And then the cyan arrow represents some place on that sphere. Now the sphere is normalized to it as a unit sphere to 1, and alpha and beta then are complex variables that enable you to be anywhere on that sphere. What's the power of this? Instead of saying I am a 0 or a 1, I can say I am in some superposition state. So when I do a calculation, it's some highly complex calculation. The additional part of the power comes in that if I got more than 1 bit, I can entangle these. So what does that mean? That I can bring 2 bits close together and I can set them into I entangle them. A C0 gate, which I'll get to in a moment, actually is an entangling function. And when you do that, it now makes it so that they are not distinguishable, and I have to choose my words carefully here, in that, you know, if I do a manipulation on one of the bits, the same thing happens on the other. And this leads to an extraordinary power. So if I use the superposition and entanglement together, and I make kind of a large entangled number. When I do an operation, it's not just doing it on one number, it's doing it on a field of numbers. So that's kind of where I'm oversimplifying this. If you want to get into it in more detail, you should read, you know, like one of the literature books, but that kind of gives you a feel for it. And then once you get into that, now you know, this is a nice way of graphically showing also this. You know, everybody's done the Young's slit experiment where you get interference. This is another thing that we're actually taking advantage of through these complex numbers. This is the experiment here, and here is the equivalent circuit where you have unitary matrices. The reason, and I'm going to specifically point out when I say unitary matrices, what that means is that it preserves the fact that you have to have the overall bit probability be 1. So when I do an operation, it preserves that unitarity or the oneness of it. There are errors associated with the qubit system. You guys are going to have to give me an education. How do I make the right panel disappear where it shows all the people?
I think you can just drag it somewhere else, but I'm not sure how to make the faces disappear.
All right, I'll just deal with it. I'll try to remember what I'm missing.
There's a little divider that you can drag to the right.
Okay. So these are terms that I'm going to introduce here. These were developed by Erwin Hahn when he did kind of one of the very early quantum experiments. Almost everything that you see in terms of language came from Erwin Hahn's paper. He's really the father of NMR. So when you get, you know, one of these MRI images, which is the popular name today, it really is an outgrowth of what he did many years ago. And he coined all these terms. And so we've got these T1, it's relaxation. So think of it as dissipation or a resistor. And it's, if I put this into the one state, how quickly will it dissipate from going from the one state to the ground state? Dephasing is what it is seeing there, where the thing can start to process, and I don't know if you guys can see my finger, but it starts to process around that sphere. And you can see the green arrows there that when I did the cut and paste here, that's not supposed to be TF, it's supposed to be T phi to match up the green arrow there. And T2 is the parallel combination of above, and the relationship you see in the lower right-hand side. So this is something that we're constantly dealing with, and it's a fundamental quantity that we end up measuring on a regular basis. When somebody says to you, the coherence time of a qubit, and right now I'm talking in very generic terms, not talking about any specific ones, they're talking about how long, what is this T1 time? What is the relaxation? So if I set it into the one state and I allow it to evolve on its own, how quickly will it then get into the ground state? You want that to be as long as possible.
Can I ask you a question about coherence? Does it mean the same thing as in optics, or is that different type of coherence?
It's a different type of coherence, because there you're talking about the coherent, well, no, it's very similar, because you're talking about coherence length, right? How long will the phase coherence be preserved?
Right.
Yeah, it's very similar, but here you're talking about, I guess you could say they're exactly the same. It's a phase coherence or a time. It's the same thing.
Thank you.
So you kind of get that. So the rule of thumb that I like to use when you're talking about kind of, and this becomes important when you're going to compare one qubit against another, people will talk about, I've got a very long coherence time. Well, how long does it take you to do an operation? Typical operation speed for us is 20 nanoseconds or 10 nanoseconds, something like that. And if I say I've got a 100 microsecond qubit, now you can just divide one by the other and tell me how many operations I can complete. 2 qubit gate would take about a microsecond, so I can only do 100 2 qubit gates and with 100 microseconds of coherence time. Why is sort of this dephasing important? Because it's that extra bit of information that I was talking about in terms of the interference. So when you want to do, for instance, the quantum FFT, that becomes critically important. So you want to make sure you retain both what is the oneness of the state, but also what is the phase information associated with it. Any questions so far? Okay. So this, I'm going to start to get more into the IBM world here. This is our view of the world in terms of the pillars of quantum computing, in terms of what we think needs to happen. And this is what guides us on our roadmap on scaling. How do we build larger and larger systems? So there's a whole series of things, and there's kind of, at the very low level, you're producing better qubits. So this is coherence, gate fidelity, high on-off ratio, when I want to separate two qubits, and I don't want one to talk to the other when I don't want to. When I do want it, I want a very high on ratio. Junction physics. So, like what kind of people might play in this area? Material scientists, in terms of gate fidelity. Gate fidelity, actually a software programmer can become pretty important in that. Improved systems in terms of packaging and integration. This is somebody like if you've done CMOS or anything like that, it's the same kinds of issues. The only thing, I think I'm going to talk about it later, when I came to IBM and I was trying to get some of the people involved here that have done standard CMOS, and they said, oh, we know how to do that. And I said, you know how to do it with Avogadro's number of electrons or photons. You don't know what it's like to deal with one or two of those. And that's where an issue starts to come in. It's where well, I'm not going to get there right now. Error correction. And so I've already told you that the bits are faulty, and so we have to figure out what are the codes, and how does that work. One of the things that I always like to tell people, if you've studied communications theory at all, and you've thought about how am I going to do, say, standard RF communications, CDMA, that sort of thing, the people that are deeply entrenched in that can talk about constellations of how they create symbols. Okay. Well, you're kind of in this space of error correction and how do I manipulate the system to go anywhere on that Bloch sphere and then do it correctly and then be able to reproduce the state. Quantum interconnects, this is where I want to take, for the people who do photonics, how do I make that coherent length very long so I can then faithfully reproduce a quantum state at a distance? That's a long-term vision. And then, kind of hardware-aware applications. And I'll get back more into that later. There's a whole variety of different technologies. I kind of paid lip service to this. So you've got trapped ions, where you will take an ion of a certain type. You'll make you take an atom, you'll ionize it. The main reason you ionize it is because then it enables you to trap it with electromagnetic fields. You can hold it in one location, you can shuttle it around and move it so you can bring two atoms close together so they can interact. There's a whole variety of levels that you can address in there that can be your zeros and ones. For quantum computing, you typically set up so that they're highly insensitive to electric and magnetic fields. But if you want to do quantum sensing, which they're also popular for, you can choose various transitions that are highly sensitive to electric fields or magnetic fields. Photons, this has been demonstrated for many, many years, where you can do different things. You can do polarization, you can do phase, anything that describes a photon, you can encode information on in a quantum way. Nanowires, they're very similar to superconductors in terms of that you're dealing with a kind of a phase slip across the junction there. Neutral atoms, in terms of neutral atoms, you do a similar thing to trapped ions. The way you trap that is by holding it in a lattice with lasers. Solid state defects, this is very popular. There's some people down in Australia. People have probably read about NV centers. You just have to create some sort of artificial system there. Quantum dots, where you actually do, you trap electrons. Single electrons, you may encode the information on the spin or the charge of that. And where I've got the red circle here, it's what we do is superconducting qubits, and you actually create an artificial atom there. And I think hiding underneath there, you see a electron micrograph of one of the Josephson junctions that we use. So the way you can think about superconducting qubits is that this is really, it's an LC circuit. But once you go superconducting, instead of being a continuum, these go discrete. I think this is on the, I don't have that on the next slide. I'll probably get to it. Let me skip it forward a bit because I think I come back.
Can I ask a question?
Certainly, go ahead.
So as a company, and maybe you don't need to represent the, the company like official, stance on this, but here we have a whole gallery of potential quantum technologies, and I know that you've got the, red oval around the superconducting qubits. But the question I have is there, like, how closely is IBM watching these other technologies? And is there any possibility that they might say, hey, look at this runaway train. It's like, it's not going as fast as where superconducting qubits is right now. But if you project ahead a few years, it looks like it may actually be, better for reasons X, Y, or Z. Either should, maybe they should invest in that development as well, or like, what is the, like, how do you decide? I mean, or is it decision already made for the next 20 years? Like, this is superconducting circuits or bust.
So okay, you've asked the exact right question, and I will represent the IBM Corporation in saying we have a lot invested in superconducting qubits, but you are correct. It would be foolish of us not to keep an eye on all of these other technologies. We are trying to start up a trapped ion effort and also an effort in some solid state type work. And so we were looking at what are other technologies, and I'm not sure we'll invest heavily in those, but as you say, it could be that you've got this dark horse that comes up from behind and you don't want to be caught unaware. So you spend a lot of time, this happens more frequently than you might think, looking at other people's technology to make sure you are following the proper roadmap. Now, part of the reason that we're in superconducting qubits is that IBM has a pretty long history in A, dealing with silicon, and B, with superconductivity. So it's a kind of a natural fit from that perspective. Does that answer your question?
Yeah, to some extent, yeah. Thank you.
Okay.
Can I follow up?
Sure, sir. Go ahead.
Then how come you neglected IBM? I mean, how did they neglect the photons? Because the first information processing in the quantum realm was actually done at IBM by Bennett, right, in photonics.
Yeah, that's also a good question. And if you look at this, scaling for photons is extraordinarily difficult, and also to perform the gates on photons is difficult. And I think that in general, IBM had a very, very large program for integrated silicon photonics, because that's kind of where you need to go for this. I don't think that went very well. And so they're kind of looking at it as, yeah, I'm just not sure that we want to invest there right now. I'm not sure that's a satisfactory answer, but
It'll do. Thank you.
Between the difficulty of actually making things scale well and perform at a high degree of fidelity, it's not as promising to IBM right now.
I guess the argument was that all these cryogenics are going to cost you a pretty penny when you install these systems everywhere. In photonics, you can literally do this stuff at room temperature. Yes, it's harder to scale, but if you do succeed in scaling, you don't have to buy refrigerators all over the place.
Very true. And, like you could, in my distant past, I was a big fan of NV centers for that, because NV centers have always promised that they could operate at room temperature, but they're not.
Chris, in an IBM machine, is the fridge actually the most expensive part, or is it the room temperature electronics?
The fridge, that's actually a really good question. They're just about, they're not quite at equal, but I'm going to say for, say, the 27 qubit system, the fridge is about $650,000, unloaded, as a single component. The room temperature electronics is maybe 200,000 for the same thing. you're not quite there yet, but you're going to get
But
there.
that scale, but in the 53-bit machine or whatever, then I guess they're pretty close to parity.
Yes. But obviously what we're trying to do, this is kind of a constant mission that runs in parallel of how do you, and you've got a double thing. You want to reduce the per channel cost and also increase density so you don't take up so much floor space. In addition, you really want to think about for distant future, so when we're talking kind of in the 1,000 qubit plus range, so between 1,000 and 1,000,000 qubits, what is that going to look like? And that's going to be where you start to push the electronics into the fridge closer to the qubits, because you've got two problems. You've got a wiring problem, and you've got a density problem in terms of control electronics. So it's going to have to be an integrated silicon solution. Other questions? Okay. So in terms of the IBM roadmap, clearly you guys have seen this picture. It's pretty darn cool. I'm actually, I don't know if you see, I'm actually in my office. I don't know if you see the kind of out the fuzzy door there. That's actually where the microelectronics research lab is that the qubits are produced in. And so I get to see all of these things. I was there, I was responsible for trying to get the photographers in and get the photos done for this lab. It's pretty darn cool. Somebody said they had a question about the big fridge. They want to,
Oh yeah, I want one. I
Okay.
want. Can I have one?
They're pretty expensive.
I know it's a stupid question, but I really.
Well, look, you got a mechanical engineering department. You guys can build this. One of the things I wanted to point out in terms of, workforce development, and, I'm not a physicist, so I can't do this. I did my undergraduate work at the University of Rochester, and this was around the time that the Laboratory for Laser Energetics was put together, which is they call it the Omega system because there are 24 beams. It's an inertial confinement system. And this entire project was dreamed up of and assembled by a mechanical engineering professor. So, you go, mechanical engineering professor doing optics and all this other stuff. Yeah, it can happen.
How many of those cryomech systems are there? Each one is like 2 watt cryo cooler.
So
I see four of the compressors.
Yeah, there's
background.
12. There's going to be 12 cold heads there.
Wow.
So there's these systems are approximately 10 kilowatts of wall power, and then at 4K they're about 5 watts of heat uptake, between 2.5 and 5, depending on the efficiency of the system.
Nice.
So I didn't import this slide well, but I was trying to show kind of a roadmap, but I've got it on a per slide basis in terms of, where are we today and where are we headed? I'm not going to spend a lot of time on that, but you can see we do have a roadmap moving out. We've got kind of an internal challenge that we want to get out to on the order of 1,000 qubits by kind of the 2023 timeframe. There's kind of a multitude of reasons for wanting to do this, and you actually want to produce larger and larger chip sizes, even though you don't know how to use them, because there's all kinds of various technological challenges of actually making these chips. Why do we want to go to 1,000? If you start to look at the error correction codes that I alluded to earlier, around 1,000 is when you can actually implement. If we were to freeze today the research in error correction codes, 1,000 qubits would give you a logical qubit which would persist for a long period of time that would enable kind of infinite computation. So we want to demonstrate that could be possible. But that's not to say that we won't develop codes that have better characteristics given as we characterize the noise.
So when you say long time, what do you mean? Because we were talking
it's kind
about
of a difficult thing. So if I said to you that, a typical error in terms of operations for a single qubit, we think we can get down to single physical qubit, we can get down to 10 to the minus 4. Once you get a logical qubit operating, you're actually, and you get it operating correctly in theory, with a distance 9 code using the color code, you'd get to 10 to the minus 11. So now you can do, So if I think about like the types of calculations that I want to do if in a classical computer, you have no errors associated with that. But imagine now that in the current quantum computers, that my errors on a physical qubit are between 10 to the minus 3 and 10 to the minus 4 per transaction. So say I do 100 transactions of that, the error in the overall answer grows quite quickly. So you want to make sure that that error is down at a low level. And I also think of that as if you left this qubit alone for a particularly long period of time, because it's a fully error-corrected qubit, it'd be sit there and constantly figure out, oh, look, I've developed an error, I'm going to fix that. So it would persist for, you know, a logical T1 time, if you wish, might be in the order of days or years.
Okay.
So in terms of the walking through the kind of things, so here with the 27 qubit system, this is our kind of a standard premium system that's allowed out there. This is the topology of the system, and I'm trying to see, you can see that the frequency distribution in this, that ends up being kind of very important, because if you have two qubits close together in frequency, because you want to make sure that you can individually address them uniquely, so you want to make sure the frequencies are relatively well separated. So then we've got our 65, and that's showing a typical frequency distribution where things are starting to get very complex. We've got 8-to-1 multiplexing on the readout, so that you don't have to bring as many wires out. That ends up being interesting and difficult. This is largely a planar system that everything's in plane right now. And until we kind of get the 3DI figured out well, you have to deal with that. So that's partly why the multiplexing is there. Now you're starting to put in additional things that I'm starting to talk about, not quite ready, but these are things that are in development. They're being actively pursued. The 127 qubit system, you've got issues now where you can get modes in the chip, so you need to make sure that you kick those down. That will be through silicon vias. There's going to be multi-level wiring and real-time classical compute, and then we get all the way up to, you know, these larger and larger density systems where you start to see the need for, so you see here, this is another thing that we're working on, high density cabling. And finally, kind of, this is where we want to be long term. So, and this is talking, when you say push the error rate down, this is 10 to the minus 4. That's what I was just talking about. For each one of those dots, you want them to be down at 10 to the minus 4. And the super fridge is kind of needed. I think we can do this in a standard fridge, and we're going to be needing the super fridge just shortly afterwards. Questions? Or keep going?
What's the RF feed out for the fridge look like at the top when you're ready to get the signals out? You must have like a gazillion number of RF feed outs.
Yes, and so that's actually one of the things that we actually have to deal with. You can see some of the wires in there. So in conventional, prior to using, for instance, this cable here, this is a high density kind of flat cable. Everything else in here are various instantiations of coaxial conductors. So yes, the density on the top of the fridge in terms of connectors is pretty high once you get up into this level, unless you start integrating the electronics in the cold stage. So this is a scaling problem.
And how are you going to mitigate because everything becomes an antenna at that level?
You know, that's an interesting question. We have not seen that yet, but so I don't have a good answer for you for that. I just don't have an answer. Sorry.
Thank you. No problem.
So then we get back to the million, and we're talking about, as I alluded to, cryo CMOS that would be integrated in the cold space, reduced qubit footprint, bigger fridge for, and we're talking about this quantum motherboard where you kind of, We have other components that I have not discussed. There's kind of qubits, but there's other various quantum bits that are in there to do signal, massage the signal if you wish, and there's some amplification. We use quantum limited amplifiers. So the question becomes, can you put that all on one big integrated, I'm calling the motherboard, but it'd probably be silicon, because silicon is something we feel comfortable working with. But there's a lot of issues associated with that. That, if you think about in terms of you get large enough scale and size, how are you going to do a CTE match between the silicon and the other devices that get cooled down? Make sure they cool down at the right rate, they don't break. I just alluded to that we've still got a large number of interconnects and connections. Anybody who's built a large scale system realizes that is the bane of existence for large scale systems. The connectors always fail. And I love this photo.
So your fridge has access from your picture, it looks like the middle part's cold, and you have room you access it from both the top and the bottom.
So you access it from both the top and the bottom. So the way this fridge is configured, yes, the cold space will be in here. Now, one of the things I'm kind of hoping is that we can actually extend the cold space, because then you can actually do interconnects in and out through the bottom. You could imagine there was a thing done at Delft, I think, recently, where they actually connected two fridge. Essentially, I think it was a microwave guide, but it was at the cold temperature. So let me talk a little bit more in detail. So I kind of started to talk about this, but I stopped myself. You can see the micrograph here. This is where we make the Josephson junction. This is kind of a size of what does a qubit actually look like. These red parts are wires that are coming in that are capacitively coupled to the qubit. These paddles here are the actual capacitor associated with it. And then this Josephson junction ends up being a nonlinear inductor. And why do I want a nonlinear inductor? If I use a linear inductor, and I already told you that the system, when you superconduct it, it quantizes. And if I come in with an RF pulse to say go from the 0 state to the 1 state, well, that's the same RF pulse that's required to go from the 1 to the 2. So if you've got a field of photons coming in, that will just climb that ladder pretty rapidly. So we introduced this thing called the Josephson junction, and the Josephson relation makes it a nonlinear. It's just two superconductors with a very thin insulator in between. And you develop, hopefully, on the part that I can't see is the equation that shows that it is a nonlinear inductor. But this is kind of our building block for everything. And honestly, it's kind of interesting that you can run this in different regimes and make it kind of operate in an analog way. But there was a large program done by IBM back in the 80s, which was called the Josephson Logic Program, where they tried to build an entire computer out of this. But you operated in a different regime. It was called single flux quantum, and you would actually trap fluxes of quantum and use the Josephson junction as switches. I don't know if any of you are familiar with that. So the, kind of why now, you can see one of the things, I started working in collaboration. I was still at BBN. I started working with IBM sort of around here. And at that time, they were around 10 nanoseconds for the qubit. But it's steadily climbed. And, you can almost say that this is showing, the standard kind of year by year increase. And so it gives us a lot of hope that we will get where we need to be. One of the things I haven't said yet, but in order for us to kind of do this full scale error correction, we're going to have to get up to, say, a millisecond or so in terms of coherence time. So we've got another order of magnitude to go there. I realize I'm getting behind time, so I'm going to kind of pick up the pace. I already talked about the fact that we use RF to excite these. Somebody pointed out that there's an antenna issue. I mean, in some ways, this resonator is, an antenna, so you have to shield things pretty carefully. But one of the takeaways I wanted people to come away from this is, there's a step in here from a workforce standpoint of if you want to navigate around the Bloch sphere and you are somebody from communications theory, and have done RF communications and that sort of thing, or software-defined radio, you can fit in really quickly in terms of those techniques and apply them to how do we do excitations. And this isn't true just of superconducting qubits, there are other qubit modalities as well. I'm not going to go into cross resonance. These are some I'm going to skip over. They're in the slide deck, and I can come back to them. This is, I'm not going to spend a lot of time on this. These are the various gates that we're actually instantiating. The main takeaway that I want you to get from this is that we have, just like in kind of standard computing, when I was an undergraduate, they said if you have a NAND gate, you can build an entire computer. You kind of create a whole series of various gates that you can then build a large system with. These are the base elements that we can build out a whole system with that we've developed. That's the main takeaway there. So what are kind of some of the challenges? I mean, somebody brought up, you know, we need to lower cost and increase density. This is kind of the standard. I was able to name this electronics. For those of you who get it, I named it Les Paul. We know cryoflex lines, CMOS control signals, attenuators, isolators, packaging, the qubit chip packaging. You know, there's a whole variety of things where people can plug in here. And that's what I really wanted for people to get away from. So the type of people that work on this project, we even have people that are, their background is polymer chemistry. In fact, somebody brought up Charlie Bennett earlier. I don't know how many of you knew that his PhD is actually in polymer chemistry. So that's kind of an oblique way to come at quantum information. I want to give a little bit of, this is a lab that I helped build. This was the first lab that we had online for doing the access. It was an interesting case. Again, there's a lot of mechanical engineering in here. I've worked with a lot of different people from all walks of life. It helps, again, if you know something about quantum. You know, there's RF generators over here. All of this stuff has been engineered by a mechanical engineer, all the pieces. How many of you, just out of curiosity, have done or logged into the IBM-Q experience? Okay, so this is just a free place where you can go. There are articles that you can read. It's meant to really help educators largely and students. There have been quantum classes that have been given and just using the IBM-Q experience. The wait times are a little long because it's pretty heavily used, and that's something we're trying to work on. You've got this thing that you can do through that interface where you get this kind of quantum score, because it kind of looks like a music score, where you kind of here you're doing Hadamard gates, X gates, the C0 gates that I was talking about, and these represent measurements where you actually do the measurement. And if you don't like that, you can do larger complex circuits, and it's programmed in we've got kind of this whole thing we call Qiskit, and there's OpenChasm as well, but I would recommend you kind of download Qiskit, which is shareware. You can contribute to Qiskit. Again, it's kind of a standard thing where if you improve it, that we just ask you that you press your improvements out to the community. But it's very Python-esque in terms of its ability to use it and what it looks like in terms of programming. One of the things that I want to press in, this is for somebody who really wants to get down and understand, like, what's the noise model? How can I look really hard at qubits? We offer this thing called open pulse. What does that mean? That means that you get way down deep into the electronics and you can program your own pulse in full shape form. You know, we have to tell you kind of what the electronics will support, but you can then say, gee, I wonder what a qubit will do if I do my pulse shaping this way. So can I do active compensation? What can I do here? Can I generate very unusual pulse sequences that will help the qubit preserve its coherence for a longer period of time? So that's a kind of a fun thing for people who really want to get deeply into this. So this is the slide that kind of really hits the system engineer and the software people. You've got all kinds of places where you can plug in this stack. But this is the full Qiskit stack. We've got the hardware living down the bottom. We've got simulators, various third parties that are working on this, all of the network, the job control, transpilers. You can work on, you can look at the algorithms, you can contribute on any one of these individual packages. So this is, again, a place where this can cut across many different people and how they can contribute. This is a circuit level. I'm not going to spend a lot of time here. These are examples you can download it and try. You can see that it's kind of very Python-esque. And how do you get started? Pretty simple. If you want, I can send you the information on this. And we've tried to divide them up in terms of what are the various packages, if you wish, for trying things out. Questions? Keep going. So one of the things I want to push on are applications, and this is another place where it is in everyone's benefit. Obviously, it's in my benefit to coerce you into working on some of these applications. There's a pitfall that I see that happens regularly with people. So these are kind of the things that we are working with internally and that we are very interested in doing. And the biggest problem we have, and this is the phrase coined by Jay Gambetta, who's our VP of Quantum, you're thinking too classically. Because there's a lot of ways these problems are currently solved on classical computers. When people come in, the first thing they try to do is say, oh, I know how to implement this. And they try to implement the same thing that you did on the classical computer on the quantum computer. And you have to say, this is something that we're going to have to teach our future people. We're going to build these systems. You've got to think about this differently. Try to exploit the underlying technology to the best of its ability. So, like, we've made a lot of progress here in terms of battery chemistry and corrosion, because those are inherently quantum problems. So you can say, oh, rather than try to approximate that like we do in classical computers, I can impress that now by creating a Hamiltonian, which describes the system, and then I can morph that into something and allow it to time evolve on the quantum system. Or I can use a variational quantum eigensolver or something like that. And the challenge is, how do we do that with these other systems? And there are ways of doing that have been published, but are they really going to get you want to make sure you get that quantum advantage. That's the real goal here. How do we get from where we are today? And so the other thing is, I say pay lip service to like differential equations and network analysis. Where does that plug into the application that you're interested in solving? Like you in your lab or your industry or whatever that is, how is that going to fit in? Yeah, I wanted to talk a little bit on each one of these. I have about one slide on each. These are published results. This is one that's been highly successful. It's battery technology. We've done a very good job at being able to simulate. The objective here is to how do you make a better, higher energy density battery. There's obviously a lot of people that are interested in this one. This is the simulation, or the thing that we're actually able to simulate. Again, is it faster than a quantum or a classical computer? Not today, but at least we're marching towards the path of that we can get the simulations to produce better results. And in this particular case, it actually turned out kind of funky that as the scientists were going through and trying to implement this on the quantum computer, they came up with a thing and they said, oh, wait a minute, this actually we can implement on a classical computer and it will improve on the classical algorithms. That's still a good outcome. Option pricing, I don't know much about this, but it's something that's obviously of very great interest. This is a partner here, JP Chase, and you can completely understand why they want to do this. I don't know if you guys have ever watched what they do, but many years ago, I was talking to a friend of mine, and you look at, oh, look, they're down, if they can see model an option and you can get something better and get an edge at like 10 to the minus 3 or 10 to the minus 4, they can make real money. And then you realize, oh my God, they move a lot of volume. Quantum machine learning is another case where we're trying to press on. This is widely applicable in a bunch of things. Again, this is like a beautiful place for a computer scientist or anyone to play. These is widely applicable to, vision problems, pattern matching of any type, all of those sorts of things. So what is required to scale? I mean, I've paid a little bit of lip service to this as I've been talking about, but like the qubit itself, I said this before, it's a single photon as opposed to, Avogadro number of photons. We still don't fully understand the loss mechanisms. So we store the energy on this little qubit. Well, there's a whole bath of kind of what are two-level systems all around here. It's almost like a cacophony or a large-scale chorus, but it subtracts energy from the system. We don't understand that mechanism. We don't know how to model it. We don't know if that's in the metallurgy or is it in the insulators. We've got some notional ways, some things that are kind of very anecdotal about what makes good systems versus not good systems. We're struggling with how do you make EDA tools. There's Cadence, there's, I can't remember the name of the other one, but they're all based on CMOS. So how do we get our tools put into those so that you can scale and build, doing 1 million qubits, we're not laying that out by hand, that's for darn sure. In terms of the machine itself, here's Micah actually working on a system down in aisle 36 for this building. There's a whole lot of issues associated with scaling. There's thermal loss. So the bottom stage where her hands are, this lands at 10 millikelvin. So if we're going to put 1 million qubits down there and you've got 1 million wires that attach this 10 millikelvin stage to this 100 millikelvin stage, okay, we have to start thinking about how do we mitigate the heat transfer between those two stages. So, or what is that system design going to look like? There's component development in terms of, okay, we've got the wires in here. We've talked about cryo CMOS. Well, there's other components that need to be in there, circulators. Maybe there's a better way of making sure that separation occurs. And I've talked a little bit when I talked about waveform generation and control. We have internal research here that's going on. And, one of the things that I would love to see us do is some sort of quantum signal processing where here's the state I want to produce. Can I make the equivalent of like a quantum Kalman filter that starts to look at where I can look at the noise on the system, and I can look at, in a standard control system, you might want to look at the covariance matrix in a Kalman filter, and then that gives you a prediction of how I'm going to do things differently. Can we do the same thing on the quantum systems? So these are kind of open questions, and I'm kind of musing, and then, bring up the big fridge. Everybody loves the big fridge. That's our CEO and our head of research sitting on that. I think this picture was also circulated. I think that's it. So, I can go through these other slides. I think I'd rather stop here and see if there are other questions that people would like to ask. Okay,
question from the audience? So I have a question. Oh, go ahead, Elias.
I have one about how universities can get involved. And the reason why I want to ask this is I actually tried to price one of those dilution refrigerators was $250,000 from a Swiss company. And that's way beyond what universities could easily afford to conduct this kind of research. Do you have any suggestions on how to do this?
Well,
the university still be engaged?
What level do you want to get engaged? You mean you actually want to do qubits? You want to do?
Well, that was about 3 years ago. I wanted to actually try to build a refrigerator so I could actually do the qubits and show my students how they work, and so that they can help fabricate them themselves.
Okay. I don't know a way around that right now. There's a few of us internally that what we're trying to dream up, we're actively trying to figure out how can we do precisely what you're talking about. How can you provide a low-cost fridge? I don't know if you're familiar with a company called Cold Quanta.
No, I actually dealt with two companies. One was called Blue Four.
Yeah, Blue Force is our predominant people. I'm surprised you could get something as cheap as $250K. The typical...
Not from them, from another company.
Okay.
Theirs was much higher.
Yeah, but we're trying to figure out, the same guy who's doing the design on this fridge is trying to think about, can we develop a low-cost fridge that could be for an undergraduate lab, and that we would actually think, you're talking about maybe producing your own qubits. I've been talking with, and we will probably end up releasing next year, small qubit systems on the order of 5 qubits.
All right.
But there is no low-cost solution. The other thing this is something I've mused on. There's this thing called Mr. Squid. Has anybody ever heard of that?
Yes.
There's a small company, I think John Clark, who was out at Berkeley, and another guy who I think is in Colorado, formed this company. I think the guy in Colorado is still doing it. And it's I would say it's an undergraduate kind of advanced lab level thing where you can start to characterize the properties of a squid. It's a little on the expensive side, but it's a high TC superconductor. And I've often thought about, could we use that as a demonstration platform? Could you create a way where you could have a 2-level splitting there? I haven't quite figured it out yet. That's another avenue that you might want to explore.
So what's so hard about installing a a quantum computer in Germany?
What's so hard about it? Installing it?
Yes, you said it's
Port
giving you a
control.
little bit of heartache.
It's all the little trivial details like import and export, and how do you get components there, and I can't travel there. Well, I am going to travel there, but that's a challenge because of the time of COVID. So there's all of these like headaches that I think if it was a year ago, probably wouldn't be as much of a headache.
Okay, so it's not the business in general of moving these things around. It's just the special times we live in.
It's the special times we live in, by and large. It's also, okay, we've installed a lot of systems in this building and also in our building in Poughkeepsie. Now, the difference between where we are here and Poughkeepsie, that's about 15 miles. Okay, so if I'm doing something, so when we first moved a system up into Poughkeepsie, you forgot something, okay, I killed an hour because I had to drive back to Yorktown. If I forget something in Germany, it's kind of like, oh crap, I have to have them drop ship it to me. I'm going to be sitting on my thumbs for a day or two. So that it's kind of like, as we plan to pack tools and things that we need and make sure that everything is in country when we want to do the final installation, you want to make sure one of my colleagues calls it packing for Mars.
Yeah, or the South Pole.
Yeah.
Okay, other questions?
I have a question. Yeah. So yeah, I was really, it's really exciting to hear about this, this qubit that's like a logical qubit that has a sign that says "Do not disturb." Qubit is in a superposition of 0 and 1 for the next year. Like that's a really amazing milestone. But one of the things that you mentioned, going from 1,000 to 1,000,000 is like, you're going to need to put everything, like all the electronics is going to have to move into the fridge, and it's probably going to be silicon. So it kind of takes me back to the question I had before, which was, you're obviously following all these other technologies, and silicon-based qubits seem to have come a long way in the last couple of decades in terms of gate fidelity, not necessarily scaling, but if you're talking about problems related to integration of heterogeneous materials, like working with silicon seems to have some benefits to it. What is IBM's analysis of where silicon is and where it's going to be, and whether it might be relevant, in the next jump to hyperspeed, going from 1,000 to 1,000,000?
So, I don't know if you guys saw the announcement. So, John Martinez, clearly a competitor of ours. He was at Google. He left Google. He's actually going to go work with Michelle Simmons in Australia, specifically on silicon qubits. So this is something we're going to end up being very interested to see where he goes with that. one thing I didn't go into that I do in some of my other talks is I talk about silicon qubits are really astounding. You're absolutely right. I mean, if you look at the coherence times, they're between 20 and 30 minutes, that's a long time. And the errors are low. What that means is that they're very decoupled from their environment, so that this again, I really glossed over a whole lot of detail, and I went very fast. But if you talk about the qubit itself and the bath of kind of other systems that are kind of all around the system that you want to manipulate, for the silicon qubit, the communication between the bath and the qubit is very low, and that makes it difficult for you to send in an external signal to actually make the operation occur. So we're tightly coupled, which means we can easily manipulate using microwaves, superconducting qubits. They're loosely coupled. So our gate times are 10 nanoseconds. Their gate times are on the order of seconds. So if you do the math, the number of operations per unit time ends up.
Why are the gate times in seconds?
Because the coupling strength is so low.
Which coupling are we talking about?
So if I want to couple an external field to cause a gate operation in a silicon qubit.
That sounds maybe for some types of gates, but like an exchange gate can be really fast.
Okay.
But I guess it depends on exactly how you're implementing these things. But it's true that like single qubit physical gate operations can be slow, but there are, for example, encoded logical qubits where you only use the exchange interaction. This was actually first demonstrated by David DiVincenzo when he was at IBM in the early 2000s. So, working with a fast gates, I think, in silicon is not necessarily a showstopper.
So when you say David DiVincenzo, that meant that was a theoretical bound.
Well, yeah, but they've been instantiated in 3.5 spin qubits.
Okay.
I think with all these things, the problem is there are many flavors of spin qubits and many gates among them. And it's hard to find one single instantiation that gets all the good stuff.
I'm thinking like not now. It's so right now it's I think it's it's looking great for the superconducting qubits. This is news to me about John Martinez. I didn't know.
I think it's really big news.
But
I think it's been really interesting to see what happens. I mean, this is, so the guy who really, it was David DiVincenzo and Roger Koch. They were people who really started things happening here. And they brought in this fellow by the name of Matthias Stefan. I don't know how many people know him. But Matthias did his postdoc with John Martinez. So it's a very incestuous community.
Okay, other questions from our audience?
Michael, I have one question. Maybe
shoot.
It's not technical. I would like to know, Chris. Really nice presentation. Is it possible we could save a copy of this talk? On
you are being recorded, Payman. Right now,
okay.
every word that you say is now
back over and over again.
Printed on classical hardware for posterity.
Because I want to, watch it again, and try to understand some of it. But like Chris, are the view graphs? Are they? Can they be shared or no? Are they?
I'll check. I think that everything I put in here is okay. I didn't get it cleared for release to send the view graphs around, but I don't anticipate that's going to be an issue.
Okay, if you can, I really would like to have a copy of it. I find it very nice to have, to go over them.
Okay.
It was really a great talk. It was I really enjoyed it.
Hopefully I didn't talk too fast.
Absolutely.
I will warn you, I did gloss over a huge amount of stuff. I went very fast, and I apologize for that, but I wanted to get a lot of it in to kind of give you a flavor for things. All right.
Thank you.
Okay. Well,
Enjoy. I'll see you all later.
Thank you.
thanks everyone for
Thank you.
coming. And I guess this is
Thank you very
this is the
much.
end.
Thank you.